This is day 9 of Unit 2. We started today with a warm-up. So pause the video, try the warm-up, and then play to check your answers. So find the inverse of A. So the inverse we find by doing 1 over 3 times 4 is 12 minus 2 times 5 is 10. So we're going to take that times the 3 and the 4, swap places, and the 5 and the 2 stay the same but change signs. So when I simplify that, I'm getting 1/2 times 4, -5, -2, and 3. And when I do that, 4 times 1/2 is 2. -5 times 1/2 is -5/2. -2 times 1/2 is -1, and 3 times 1/2 is 3/2. That is A inverse. Okay. So today we started our lesson by picking up where we left off from yesterday's lesson. If you recall yesterday's lesson, I showed you how to find the inverse and find the determinant, but we didn't really talk about why we were finding them. I just showed you how. So we're going to get into a little bit today of why, but before we can get into the why, we're going to first look at a few identities that you know from math, from your earlier years of math. So we have the additive identities, and I'm going to show you first how that looks with numbers, just to refresh your memory, and then I'll apply that to matrices. So if I have a number, 5, let's say, if I add the additive identity to it, I should get the same number back. Identity means self, so same number back. So we know that that means that the additive identity is 0. So that is the additive identity. Okay, when we're talking about numbers. So in terms of matrices, if I have a matrix, 1, 2, 3, 4, times some matrix, or I'm sorry, plus some matrix, when I add those, I'm going to get the same matrix back, 1, 2, 3, 4. So we know that the additive identity for matrices is going to be a matrix with all zeros in it. Okay, so that's the additive identity for matrices, is a matrix with all zeros. Now, multiplicative identities. We talked about this just a little bit yesterday. If I have a number, 5, and I multiply it by its multiplicative identity, or the multiplicative identity, I should say, I get back the same number that I started with. So we know that number is 1. So the multiplicative identity in terms of numbers is the number 1. So we also know that if we start with a matrix, there's a matrix that I can multiply this original matrix by to get the matrix that I started with. Okay, and that matrix is the matrix 1, 0, 0, 1, which remember we called I yesterday, I standing for the multiplicative identity matrix. Now this is the 2 by 2 multiplicative identity matrix. So when we multiply a matrix times I, we get the matrix back. So this is also true for 3 by 3s. So if I have a matrix A, B, C, D, E, F, G, H, I, if I multiply it by the 3 by 3 multiplicative identity matrix, I should, as a product, get the same matrix I started with, A, B, C, D, E, F, G, H, I. So the question becomes, well, what matrix is the multiplicative identity for 3 by 3s? So we're going to figure that out. To figure that out, we're going to start with the 1, 1 spot. the 1, 1 spot comes from the first row of the first matrix times the first column of the second matrix. So I know when I multiply each one of these in order from left to right, top to bottom, I'm going to add then, I should get a result of A. So A has to be multiplied by, in order to get A, a 1. B and C, though, I have to multiply them by something, but there's no B and C in that 1, 1 spot, which means B and C both get multiplied by 0. So A times 1 is A, B times 0 is 0, C times 0 is 0. When I add 0 plus 0 plus A, I get A, which is what I'm looking for. Similarly, if we're looking at the 1, 2 spot, the 1, 2 spot comes from the first row of the first matrix and the second column of the second matrix. So A times something, B times something, and C times something, all added together should equal B. Well, that means the 1 has to be there because B has to be multiplied by 1. A and C both need to be multiplied by 0. So lastly, the 1, 3 spot comes from the first row, third column. So A times something, B times something, C times something, and we want C to be the result when we add those 3 products. So we know C is the one that has to be multiplied by 1. A and B both need to be multiplied by 0. So the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, that is the 3 by 3 multiplicative identity matrix. Okay, and then you can start to see a pattern here if you're comparing the 2 by 2 and the 3 by 3. And you can see the 3 by 3 is made up of the 2 by 2. It's right here. Okay, but we just add a 1 in the diagonal and zeros. So the 4 by 4 or the 5 by 5 or the 6 by 6 I matrix would have 1s going down this diagonal and zeros everywhere else. Okay, so now we're going to take a look at how these identities are going to help us to solve an equation. And we're going to start with a linear equation. Okay, we're going to start with a linear equation. Let's see here. So we're going to start, separate that a little bit. So if I wanted to solve something very, very basic, like 5x equals 10. Okay, well, we know to solve that, we would divide both sides by 5. However, in a moment, we're going to take a look at how this relates to matrices. And with matrices, there is no such thing as dividing. We don't have a dividing process with matrices. So in this problem, I want to solve this without dividing by 5. So if you think back to what you know about what you learned in previous math classes, plus what we talked about yesterday with numbers, you'll hopefully realize that instead of dividing by 5, we could also solve this by multiplying both sides by 1/5. Okay, and the reason that that's helpful is, well, first of all, 1/5 is we talked about this yesterday, the multiplicative inverse of 5. 1/5 is a multiplicative inverse of 5. So when I multiply a number times its multiplicative inverse, 5 times 1/5, I get 1. And 10 times 1/5 we know is 2. Now, so we took a number times its multiplicative inverse and we got 1. And 1 times x we know is just the same thing as x. Okay, because 1 is the multiplicative identity. Okay, so that's how we were able to solve that very basic linear equation. We multiply both sides by the multiplicative inverse of the number, and then we have 1, which is the multiplicative identity, times x, which just means we get x because anything times 1 is itself. So now we're going to use that same idea on a problem, an equation involving matrices. So go ahead and put that matrix equation into your notes. Okay, now I have a matrix here times x, and I notice that's a capital X, so I know that means x is a matrix itself. And then I have another matrix. So just for clarity's sake, we're going to call this first matrix A, and then we have x, and then we're going to call this other matrix B. So we have A, x equals B. Very similar to 5x equals 10, the linear problem we just solved. So I can't divide both sides by A because there's no such thing as dividing by matrices. But what I can do is multiply both sides of this equation by the multiplicative inverse of A. And we talked about that yesterday, how we write the multiplicative inverse of A. That's just A inverse. So I'm going to multiply both sides of the equation by the multiplicative inverse of A, or A inverse. Now, when I go to put the A inverse over here on the right side of the equation, you have to be careful, because if I were to put A inverse here on the right side of B, think about that. B is a 2 by 1. Okay? And A inverse is going to be a 2 by 2. So if I put B first and then I put A inverse second, the dimensions are not going to match up. So I'm not going to put A inverse here on the right side of B. I'm going to put it on the left side of B, because then I'll have a 2 by 2 and a 2 by 1, and then the inner dimensions will match up. So that's what I'm going to do. So now that I've done that, well, we're going to kind of break this down so we get x all by itself. So we have A inverse times A. Well, we just talked about that in the last problem with numbers. 5 times 1/5 is 1. Well, in matrices, a matrix times its inverse, its multiplicative inverse, we remember from yesterday, that equals I, the identity or the multiplicative identity matrix. So I have Ix equals A inverse times B. And I, the multiplicative identity, is like 1. So the multiplicative identity matrix times x is equal to just the matrix x itself. So now I have x all by itself. Okay. So this is the process that we're going to follow now so that we can solve our matrix equation for x. We're going to find the inverse of this first matrix, and we're going to multiply it by the second matrix B. And that will give us x, which is going to be a matrix. So let's go about doing that. So I'm going to find A inverse. Well, A inverse, I'm going to do the determinant, and I'm going to put that under 1. So 1 over 2 times 4 is 8, 7 times 1 is 7, 8 minus 7 is 1. That's easy enough. So we have just 1 times, and now I'm going to interchange the 4 and the 2, change the signs on the 1 and the 7, and when I multiply 1 times those, I just get those. So that's A inverse. So now we need to solve for x. So x is that matrix, A inverse, times B, and B is our 1, 4 matrix. Okay, so we're going to go ahead and multiply those. So we know a 2 by 2 times a 2 by 1 is going to equal a 2 by 1. So I have the 1, 1 spot, which means 4 negative 1 times 1, 4. So 4 times 1 is 4. Negative 1 times 4 is negative 4. So 4 plus negative 4 is 0. Then the 2, 1 spot, negative 7 times 1 is negative 7. And 2 times 4 is 8. So 8 plus negative 7 gives us 1. So that means x, the matrix x, is equal to 0, 1. Now, just like with linear equations, just like 5x equals 10, and if I got solved and got 2, I can check that by substituting 2 back into the equation. Same thing here. If I wanted to, I could substitute 0, 1 up in this equation for matrix X. And then I'd multiply this matrix 2, 1, 7, 4 times 0, 1, and I should get 1, 4 when I do that. Okay. All right, this one. Go ahead and get that in your notes. Now, this looks a lot more complicated than it actually is. So to make it look like something you're more familiar with, everywhere I see a matrix, I'm just going to put a number instead. So that first matrix, I'm just going to put a 5 there and then an X, minus sign. This is a matrix, so I'm just going to put a number, 3 let's say, equals a matrix times X, so how about 2X, and then plus sign, and then a matrix, so just a number, another number, 5. So if I'm trying to solve that real basic linear equation, we know that's pretty easy. So what would we do first? Well, we'd probably add 3 to both sides first. Okay, so now let's take that same logic and apply it to this matrix equation. So that means the first thing I would do is add the matrix 2, 4 to both sides of this matrix equation. Now, notice when I'm putting the 2, 4 and I'm adding it, I'm intentionally putting it below the matrices that just have numbers, and I'm not putting it below the matrices that have an X. Just like with our linear equation, I would add 3 to the numbers. I wouldn't try and add it to the variables, to the 5X or the 2X, because they're not like terms. So same thing with matrices. So now I have on the left 3, 5, 1, 2. X is equal to 1, 2, 3, 4 X plus, and now I'm just going to add those two matrices. So 3 plus 2 is 5, and negative 2 plus 4 is 2. So just like our linear equation over here, where we would next probably subtract 2x from both sides, we're going to get this x over to the other side by subtracting it. From both sides. So on the right-hand side equals, I have just the 2 by 1 matrix with 5, 2 in it. And on the left-hand side, I'm going to subtract these now. So I have x on the end there. And I have 3 minus 1 is 2. 5 minus 2 is 3. 1 minus 3 is negative 2. And 2 minus 4 is also negative 2. So now I have an equation times x equals, or a matrix times x equals a matrix. So I'm going to label that the way we did in the last problem, ax equals b. I'm going to again write the proof for solving it, and I do want you to show that each time. So I can't divide by a, but what I can do is multiply both sides by a inverse. So then I have a inverse times a, which equals I, or the multiplicative identity, times x equals a inverse times b. The multiplicative identity times x gives me just x, and that equals a inverse times b. So that's exactly what we're going to do. We're going to find a inverse, which is the inverse of this matrix here. So let's do that first. So I'm going to take 1 divided by the determinant. So that's 2 times negative 2, which is negative 4. Subtract negative 2 times 3, so minus negative 6. And we'll multiply that by flipping the negative 2 and the 2 and changing signs on the 3 and the negative 2. So that gives me 1 over 6 plus negative 4 is 2, 1/2 times negative 2, negative 3, 2 and 2, which gives me negative 2 times 1/2 gives me negative 1. Negative 3 times 1/2 gives me negative 3/2. 2 times 1/2 gives me 1 and 1 again. So that's A inverse. So now I'm ready to solve. So back to my equation here. X is equal to A inverse, which we just got, -1, -3/2, 1 and 1, times B, which was 5, 2. So let's go ahead and do that. So we have a 2 by 2 times a 2 by 1, which is a 2 by 1. First row, first column. -1 times 5 is -5. -3/2 times 2 is -3. -5 minus 3 is -8. 2, 1, second row, first column. 1 times 5 is 5, and 1 times 2 is 2. 5 plus 2 is 7. X is equal to -8, 7. So again, I could check that if I wanted to by substituting it back into the original equation, and I would see that X is a matrix with -8 and 7 in it. Okay, that's it for the lesson for today. Homework is page 26 and worksheet number 6 in the worksheet booklet, of course, unit 2.